Hey there. So we're going to keep talking about series. As I said, that's what chapter 11 is going to be all about. And we're going to talk about some of the different ways to tell if a series is convergent. And we looked at geometric ones, and we looked at using a limit to just test for divergence in our last lesson. And now we're going to talk about something called the integral test. Because now that you've gone through a couple of years of calculus, you have a lot more skills to use to test these different series. And if you're wondering why are series taught with calculus, well, remember that integrals are series. These two ideas represent the similar idea. Sigma is just the Greek for S, and this looks like an S because it stands for a sum. So get yourself ready for notes, and we're going to talk about the integral test. Now, here the idea is, say that we have a infinite series that is convergent. If I graphed this red function here is f of x is equal to whatever those terms are. So that's the idea here. And now what we have then, if we look at each of these points on the graph here, if this down here is x equals 1, 2, 3, 4, 5, 6, etc., what we can say here is that this area of this box here, the upper bound is a1 because its length, its height is a1 based on the function, and its length is 1 between 1 and 2. This left-hand Riemann rectangle has an area of a2, a3, 4, 5, and so on. You'll also can tell the right hand, if you wanted to give yourself a lower bound of a function, this has an area here of a2, a3, a4, and then here would be the a1 with the bound at 0 if we decided to do it that way. And so the idea here is that if the integral of the function converges, meaning that it approaches a number when you use improper integration techniques, then the series converges. Because if you look at here, the value of the series is a little bit less than the series here, because it's this plus here all the way down. So you can see that that's an underestimate of this convergent graph. And it has to have this concavity at some point because it has to approach 0. Alternatively, if the integral diverges, means it goes towards positive or negative infinity, then the series diverges because it's also, it can be constituted as an upper bound of the function depending on if we're starting at 0 or if we're starting at 1. And so we know that these will have matching behavior. So in number 1 here, determine if the series 1 over n squared plus 1 converges. So we're going to be using the integral test. So we want to consider the integral from 1 for our lower bound to infinity of 1 over n squared plus 1 dn. If you want to change the variable to x, because that's something that just our brains naturally do, that's fine. Now, hopefully you would remember that this is tangent inverse of n. Yes, the terms are in a slightly different order, but that will not affect our integral from 1 to infinity, which we want to find as the limit as b approaches infinity, and b is right there. So we're going to consider the limit as b approaches infinity of tan inverse of b minus tan inverse of 1. Now, hopefully you remember tan inverse of 1 is pi over 2. Tan inverse of b, if you think about, I'm going to draw a graph over here on the left-hand side. If we have a graph of tan inverse, this is going to be the shape, and it has two horizontal asymptotes, which is why you're going to see it come up in a lot of these problems involving limits at infinity, because it has limits at positive and negative infinity. This limit at positive infinity is pi over 2, and negative pi over 2 at negative infinity. So here, this limit is then equal to pi over 2, not pi over 2 here, pi over 4, because that is where the tangent of is equal to 1, because remember that's the same as tangent inverse of 1. So pi over 2 minus pi over 4 is pi over 4. So what that means is that it converges, because that is a constant number and not plus or minus infinity. Now, it's not going to converge to that number. This series is not equal to that number. It's equal to a number that is close to that number. All right? It is equal to a number that is slightly more, because as we look here, A1, A2, A3 are all slightly more, since we're starting at the bound 1. So if you were asked, for example, which of these, this is a common AP question, which of these could equal this? You want to prove that it converges, and then they'll show you pi over 4, and then they'll show you something a little bit more than pi over 4, and you want to pick the greater number. Now, you might be asked to estimate this to the nearest tenth. If you were asked this question, you were going to do it on your calculator. So for most of you on your calculator, if you're using the TI 84 Plus, the nice thing is that if you go to math, you are going to have a place already to just enter in your sigma information, and it's going to be in the first part of that math menu. So it's going to be still underneath math, and it's going to be the summation sign, might say sum. Now, for those of you who don't have a TI-84, if you've got a TI-83 Plus, which is the other really common calculator, what you're going to want to do is you're going to use the second function on the list. So that's on the stats button. Go to list. And then from there, you're going to want to go to math. Sorry. You're going to want to go to math. And that's where your sum option will be. So if you're using this character, you'll just automatically get this. You'll start by entering in the bottom, and then you're entering in your function, 1 over, it'll supply you with whatever variable you're using, whatever mode you're in. Now, if you're using this, what you want to do is sum, and then parentheses, and you're going to want to go back, and you're going to go to second list again. So second function on the stats button, which is list. You're then going to want to go to the options, OPS, which is next to math. And then you're going to want to use the sequence, because that's going to be a list of numbers. So it's the sum of the sequence. So if you're using an older calculator, you're going to want to do that. Type in the function, just as we saw there. Right? And then what you want to do is comma x, comma 1. So now these are displaying the same amount of information. Now, on your calculators, you can't plug in an infinity sign here, and since it says to go to the nearest tenth, you just want to pick a number in the upper bound that you're like, I think that's probably going to be pretty good. So in this case, I would pick 100, and you can type that in, and when you click enter, it will give you a number, and it'll be 1 point something something something. Now, we don't know if it's accurate to a tenth yet, so what we're going to do is just click second and enter, and that's going to repeat this, and I'm just going to delete this number, and I'm going to say, okay, well, is it the same for if I plug in 200? And if that 10th digit, once that 10th digit stops changing, which you should get 1.1, that's when you know you're rounded to the nearest tenth. All right, let me know if you have questions about using your calculator or about using the integral test, and I'd be happy to help you with either device. If you don't have a graphing calculator right now, or you don't know where yours is, please get in touch as soon as possible. Talk to you later.